Okay, hello everyone. So, uh, I have again shared my screen and opened the slides. So hopefully you can see the screen and you can clearly hear me. If not, let me know. Uh, if you cannot if you cannot see the screen or the slides. So last time we were basically talking about jump and call instructions. We had completed our discussion about three kind of jump instructions, which are like jump, which is basically absolute jump, relative jump, or R jump, and then indirect jump, right? And then we had just started our discussion about call instruction, but we had not enough time to go deeper into it. So let me today just give you the brief background or the brief recap of what we did. We talked about in the call instruction, and then we can take it from there. So the first thing is that uh, for the call instruction to work properly, we need a data structure named stack. Why we need it? Because whenever a function A is calling function B, so uh, the return address, which is basically the next instruction in the sequence of so if you have, let's say, a function A, and this is, let's say, body of function A, and here you make a call, right? And then you have a next instruction. So if you are making a call to function B, so once we are done with the execution of function B, we need to know that where the execution need to start after completing the execution of function B. So which is basically this address, the address of this instruction, the next instruction in the sequence after the call B, right? So we need to, for that, in order to like find out where is the return address, so we need the stack data structure, right? So we'll see how we use it in example. But for example, for now, let's focus on the stack data structure itself. So stack is a last in first out data structure, which basically mean that the item which you place on the data structure, like the last item that you place on the stack data structure is the first item to be retrieved back. So and how we know the current position of the current position of the next empty element, or next not empty element, actually next empty location in the stack. For that we use uh, a stack pointer, so it always points to the next empty location in the stack, uh, not in stack pointer, in stack. Okay, so here in this figure, we have initialized the stack pointer to 0x7ff to point to the largest address in 2 kilobyte RAM SRAM of AVR. Why? Because what we actually I explained it last time, but let me do it again quickly. Yeah. So let me do it quickly again today. New page. State. So in Avian microcontroller, at least in at Mega 328 328p, the total size of your memory is 32 kilobyte, right? So it's mean that you have, so 32 kilobyte basically means equal to 2 raised to power 5 and into 2 raised to power 10, right? So you have 15 bits to 15 bits to address any location in the memory, right? So if I have 15 bits and I set all of them equal to 1, so I get uh, uh, yeah, sorry, my mistake. So 32 kilobyte is basically your 32 kilobyte is basically your code memory, right? The program memory, right? But stack is not existing in the code memory. It exists in the data memory, right? It exists in the data memory, and size of the data memory is 2 kilobyte, right? In the microcontroller at Mega 328p, right? So take 2 kilobyte is basically, so this is wrong. So 2 kilobyte basically mean 2 raised to power 1 into 2 raised power 10. So these much bytes, because 1 kilo is 2 raised to power 10, right? So you have 11 bits, and basically it means you have 11 bits to make an address. So if you have 11 bits and you set all of their values equal to 1, so you get something like this in binary, uh, right? Uh, so we have 8 and 9 and 10 and 11, right? So we have 11 bits with having a value of 1. So if I convert it into hexa, so it is 0x3, sorry, 0x7ff, right? So this is 0x7ff is basically the address of the last location in my 2 kilobyte memory, and 00 is address of the first location in the 2 kilobyte memory, right? So we are saying that actually we can have stack pointer to point anywhere in this range, anywhere, right? But it is a convention that we set the stack pointer to the last address in the 2 kilobyte. Why? Because the memory on the lower side, it may have already been used, right? For example, the global data, the variable which are globally initialized, they are placed on the lower side of the memory, right? So since we are talking about a microcontroller, there is no operating system, everything we have to control as a user programmer. So we need to make sure, like for example, if we are setting a stack pointer such a way that let's say it points to a location in the memory, it should not point to a location which has already been used, right? Even like if I'm setting stack pointer equal to 0x7ff and is pointing into this location, I need to make sure that my program is not using it in the same location for holding multiple data, because then I will be overwriting my own data and I will lose my data. So the program will not work in a way I want it to work. Okay. So this is convention that stack pointer is initialized with the last address in the memory range, in the data memory range. Okay. So that's why here in this figure we have stack pointer. Let me make this correction right now, because last time also I was saying that stack pointer. Let me just move it here so that then text and the figure, they are uh, synchronized with each other. They are not saying two different things then. Okay. So uh, now you know why we are initializing stack pointer to 0x7ff. Also, as I said, the global variables, they are allocated. AVR compiler allocates them from the address on the lower side, like 0x100. So which is the lowest data address. So that's why lowest data address, because remember our general purpose registers and our special function registers, they are also in the data address range, right? So uh, we need to be careful that when our stack is too low, basically it means that stack pointer points to a location which has a lower address. So for example, this is the higher address, 0x7ff, the maximum address. But if stack pointer points to a location that is too low, then it can potentially override global data and cause serious issue. So we need to make sure that we are not overwriting anything when we are pushing data on the stack, so we don't end up corrupting our own data. So stack pointer here, it is a basically an 8-bit register, sorry, 16-bit register, and it has two components, or it consists of two 8-bit registers, stack pointer low and stack pointer high. Uh, and this is the address of these two registers, SPL and low and SPL. IO address range, you can, yeah, they have the address of 0x3D and 0x3E, but if in the overall memory, data memory, the address is 0x5D and 0x5E. Okay. So how we access the stack? So whenever uh, we want to put some data element on the stack, so that operation is known as pushing the data on the stack. And for that, we have the push instruction in the AVR microcontroller. So you only need to execute this like push and then specify a register, right? But when as a part of execution of this instruction, what happens that microcontroller it actually puts the value of that register on the top of the stack. So for example, our stack pointer is pointing here. So when I say, let's say push R1, whatever value of R1 has, that value will be written here. Let's say the value is X. So the X will be written here and then stack pointer will be incremented. So these two operations, they will be performed as a part of the single instruction push, right? So here when I'm saying incremented, actually it is decremented. Why? Because our stack grows downward. So every next look at when we say downward, every next location has a smaller address as compared to the previous location. Okay. Uh, Pop instruction, actually it does exactly opposite of what the push instruction is doing. The push pop instruction actually retrieves the data from the top of the stack. And when we say top of the stack, it's mean the location, the last filled location, right? So remember when we said that stack pointer always points to the next empty location, right? So when we say pop, it's mean that the location to which is pointed by stack pointer is empty. For example, this location is empty, right? So that's why when we do pop, we first have to increment stack pointer so that it points to the last filled location, which is the location holding the data X in this particular case, right? So that's why we are first incrementing it by one, and then whatever value you have in that memory location, basically stack pointer points to a memory location. So whatever data you have in that memory location, you put it in the RD register, destination register. Okay, so other than this push and pop instruction in this slide, we are basically here we have these two instructions which are reading the value of the SPL and SPH SPH registers into R28 and R29. So 0x3D is actually the address of SPL register in the IO address space. So you can use the in instruction and you can say, okay, read the value of the lower 8 bits of the SP register into R28 and read the higher 8 bit of the SP register in the R29. And these two registers together, 28 and 29, they are known as the Y register in the assembly. So if you use Y in some instruction, so it will basically mean read the 16-bit value from R28 and R29. So why we are using them here, or why we have these instructions in this slide, because we are going to use them in another example later on. So I just want to take them, clarify them at this point. Okay. So any questions? Okay, now let's have a look at how when we execute a program which is using the stack by performing the push and pop instructions. So how the content of the memory are updated, right? So uh, again, the first column give us the address of the instructions. On the right side, you have the instruction itself. And here on the left side, we show four registers R0, R21, R20, and R22 because these are the registers which we are going to push or pop from the stack. And here on the bottom, we have stack. So stack is again, it is just a memory location. So our stack pointer is, let's say, initially pointing at the location 000, all zeros, right? Remember what I said, we can make stack pointer to point any location in the memory, in the data memory. But the convention is that we always make it point to the last or the location which has the highest address. However, to keep things simple in this example, we are not doing that. We are setting stack pointer to all zeros so that it is easy for us to understand. Otherwise, if I use the address 0x7ff, then it will be like we need to do the subtraction or addition, like increment, decrement, and it will be not easy to track the things. Okay. So so first we have PC is equal to 0. So here what we are doing is we are saying load immediate in R16 high RAM. And so high RAM, and actually this is of how this name it, macro. This is a macro which is defined in a header file, right? So when we use this kind of macro in an actual program, we also need to include that header file. So we have an example at the end of the slides where we do so. So don't worry, you will see how to include that header file, and it is also mentioned in book. So if you when you will read the relevant section of the book, you will see what is the name of the header file which you need to include, right? But here what we are basically saying is that uh, load the high byte of the last address of the RAM or data memory in R16. So for example, remember I told you what was the address in our case? The address was 0x07FF. That is the 16-bit address, right? So initially, when you don't at the start of the thing, start of the world, stack pointer points to the zero. But now you want to modify it so such that our stack pointer points to this location. So this is RAM end, right? So here we are saying that load the high byte of the RAM end in the R16, which basically mean put 07, 0x07 in R16, right? And then uh, we are saying, okay, now move 07 into SPH, right? So if initially, if I draw it here, let's say, so if this is my SPH and this is SPL, so initially both of them were 00. I'm not writing. But after saying this, now out R16 to SPH, what will I get here? Here I will get 0x07. I'm not writing 0x, but here I will get 07. And then next I'm saying, uh, so, but remember SPL is still 00. So it means stack pointer is now pointing somewhere in the memory, which is, and the location is not 0, right? And then I'm saying, okay, now load the low end of the RAM and low byte of the RAM and in R16. So basically I'm saying load this address 0xFF, right? So what will happen is that it goes to R16 and them saying write R16 to the SPL. So here you will get FF. Definitely, it depends what is the value of your macro RAM and high RAM and lower RAM. And I'm assuming that it is 0x07FF. But let's say if you are using an AVR microcontroller, which gives you more than 2 kilobyte, let's say 4 kilobyte. So the last address will not be 0x07FF. It will be 0x08FF, right? So now your stack pointer points to the, once you have loaded it, stack pointer points to the last location in the memory. Okay, so next what we are doing is that we are going to load a bunch of values in the register R20, R21, and R22. So now R20 is set to 0x10, then R20 is set to 0x20, and R22 is set to 0x30, right? Now we are going to, what we are going to do is that we are going to push the values. So we have these values in registers here now. 10, 20, and 30. Now we are going to push these registers on the stack, and we will see how things happen in the stack memory. So when you say push R20, so remember what happened first. Whenever you do push, stack pointer always points to the first empty location. So it's mean that we can put R20 value of R20 here, but then after that we have to decrement the stack pointer so that it points to the next empty location. So when we say push R20, so R the value of R20, which is 10, is written in the stack memory, and then the stack pointer is decremented so that it points to the next location. Then when you say push R21, so the same thing happened. The value of R21, which is 20, will be placed on the stack, on the top of the stack, and the stack pointer will be incremented, right? And now when we'll say push R22, the value of R22 will be written on the stack, and the stack pointer will be decremented again. Okay, now we are done with the push. Remember, the push and the pop operation, they are done in the reverse order. Reverse order mean, like for example, if you uh, in this example, what we are doing is like we are popping the value into R21. But if we which basically mean that the R30 is the value of value coming from R22 register, right? So, which basically mean that we are popping value into a different register. However, if there is a situation where we want to save the registers in memory and then want to restore them, then we should do the push and pop in like exact reverse order. For example, here if we are pushing R22 as the last register, then R22 should be the first register to be popped. For example, when we make a function call, so first if we are storing, when we enter the body of this function call, so we are saving some registers in the memory. Let's say we are saving register R20, R21, and R22, And then when we do the return, before doing the return instruction, we need to pop them in the same reverse order. So we'll first say pop 22, pop R21, pop R20, R20. Okay. So here now, but here we are saying pop R21, so which basically mean that the value which we have on the top of the stack, it will go to the R21, right? But again, when we do the pop, what we do need to first, because stack pointer always points to the empty location, so we first need to decrement it so that it points to the first filled location, and then read the value from there, right? So when we do pop R21, so what happens, that first stack pointer is decremented, and then the value is written to, is placed to R21. Now when you will say R20 pop pop R0, so the next value on the top of the stack will be moved to R0. But again, you first need to decrement the first you need to update the stack. Maybe it's better to say the word update, because when we are it is going downward. So when we are pushing, we need to increment, we need to decrement, but when we are popping, we need to increment the stack pointer. Anyway, so here we are, when we say pop R0, so stack pointer is now incremented and the value is written to R20. And when you say pop R20 now, again, it will be, stack pointer will be first incremented, and the value will be then read from that, the location which is pointed by the stack pointer. It will be read from there and put in R20. And then we are entering an infinite loop here. Okay. Any questions? Any questions? No? Okay. So how we use the stack when we make a function call. So to make a function call, we can actually use four different kind of instructions in the AVR microcontrollers. Call, R call, or a relative call, I call, or indirect call, and then there is another one which is called EI call, or extended indirect call. So we will discuss each one of them in detail, but let's first focus only on call and recall. So the thing is, like, you use this instruction call whenever you want to make a subroutine, whenever you want to call a subroutine or a function. And and you can also use rcall. The difference between these two is like how far they can jump, like the destination function which you are calling, how far it is located from the current location, right? So we will discuss that in a separate slides, but for time being, let's focus on how how stack is used when make a function call. So during a function call, what happens, that the address of the next instruction is placed on the stack. So next instruction basically mean the instruction which is in sequence, in sequence in the body of the function which is calling, actually, which is making the function call. So for example, this function, let's say we have this code and it is making a function call here. So this is next instruction, increment R20, right? So when you will say call function name, so what will happen, that address of this instruction increment R20, it will be first loaded or pushed on the stack. And then also, as a part of execution of the function call, or the call instruction, what will happen is that PC will be loaded with the function address, which is basically the address of this label function name, right? So now let's have a look at how things change when we make the progress. We are skipping these first four instructions because they are doing the same thing which I explained earlier. They are initializing the stack pointer, initializing the stack pointer with the address of the last location in the data memory. And then when you say, then we are loading two values, 15 in R20 and 5 in R21. So not a big deal here. So when we come to the next instruction, call function name. So this is like where we want to focus our attention. Uh, So when this call instruction is executed, the address of next instruction will be loaded on the stack. And what is the address? The address is 000008, right? And the second thing is that PC will be loaded with the address of this label. What is the address of this label? 00A. So actually, this address is part of the operand of the machine code of the call instruction. So if we look at the machine code, so here we have already the address of the operand, right? and by operand we mean the label, right? So so what happens is that that the address of the next instruction, which is 0008, is placed in the stack, and your PC is set equal to the value of the operand or address of the function, so which is 0008. 0008. One thing which just want you to just I want to highlight is that when you are loading this address 008 into the stack, pushing it onto the stack, it always the higher bytes are pushed first. So what is the higher byte? Higher byte is 00, right? So first the 00 is pushed to the stack, and then the lower byte of the address, which is 08, right? And when you will be popping, what will happen? That lower byte will be first popped off, and then the higher byte will be popped off from the stack. Okay, so if now PC is set equal to 008, it's mean our next instruction that will be executed will be from this address, right? So which is basically nothing but we are saying, okay, add two numbers, and then our program counter increments in a sequential fashion, so it becomes 00B. And then we are saying return, right here. This is now we need to focus on the instruction return. So uh, when you execute the return instruction, so what happens is that the 2 bytes from the top of the stack, they are popped off and placed into the program counter. So first the lower byte will be popped and it will be placed in the lower byte of the program counter, and then the higher byte, which is 00, will be popped off and then placed in the program counter. But you don't need to have separate pop instructions to do that. All this is done as a part of the execution of return instruction. So when now PC is set equal to 008, it's mean that next instruction that will be executed will be the one which was in sequence in the body of the caller function, right? So which is increment R20. And when that is executed, PC is incremented by one again, so which points to the next instruction, which is an infinite loop. Okay. Any questions? Is everything clear? How call works and how uh, it pushes that return address on the stack, and how return pops off the address from the stack to give the execution control back to the caller. Okay. So if no questions, then let's continue with our next slide. So the question is like how we can pass the function parameters or arguments between C and assembly. So let's say you are writing a program, right? And you have a function, let's say function A, which is written in C language, and you have a function B, which is written in assembly language. And A is calling B, right? So when A function A is calling B, it need to pass some parameter to the function B, which is written in assembly language. Now we know that in higher level languages, how parameters are passed, but how the parameters are passed from a function A, which is written in higher level language, to a function B, which is written in assembly language. So parameters, they are passed by using 18 registers, and those registers are R8 up to R25, and these registers are typically used in pairs. In pairs mean that R8 and R9, they will be used in a pair, and then R10 and R11, they will be used in a pair. And the parameters are passed in order, R24 downward to R28. What does it mean? So wait a minute, let me explain what it means. No. So let's say you have function A, which is written, let's say, in C language, and you have function B, which is written in, let's say, assembly language, right? And let's say here you're making the function call, and the values you are passing are like, let's say you are passing some uh, two numbers, right? Let's say you are passing 10 and 11, right? So I don't know, maybe the function which is written in assembly, it maybe adds those number, right? So the thing is like uh, these parameters, they will be passed to the assembly language using registers, but they will be, these registers will be used in order. So what are the registers? The registers that are used are R24 downward to R8. So which means that uh, R24 and R25, remember I said they are used in pairs. They will be used to hold the value of 10, right? So actually it means the 16-bit value of 10, 16-bit value. And then R22 and R23, they combine hold the 16-bit value of next parameter. Okay. So which basically mean that on your assembly side, in your assembly program, if you want to access the first parameter, you should look at the value of combined value of R24 and R25. If you want to look at the value of the second parameter, you should look at the combined value of R22 and R23. So there is like they are placed in they are passed in order. The first parameter will always go to R24 and R25. The second will go to R23 and R22 and R23. And if you have more, they will go to the next pair. Okay. So that is what we mean by that parameters are always passed in order. Downward to R24, downward to R28. So additional, let's say, so maximum we have 18 registers, so which mean basically 9 pairs. So we can use maximum in maximum we can pass like 9 parameters from function A to function B in our example. So what if we have additional parameters and which we want to pass from A to B? Then what we do is that we can put them on the stack. They are placed on the stack. We don't put them on the stack like when we compile our program in C, and we tell our compiler that we are calling an assembly function. So the compiler will automatically place them the first 9 parameter in those registers, right? And if there are more than 9, they will be placed on the stack. Now it is the job of our assembly program to know that which pair of registers should look for, let's say, for the first parameter, for the second parameter, for the ninth parameter, and how to read the additional parameters, like say parameter 10 and 11 from the stack, right? So here is an example, a very simple example. Later we have an example where we are passing more than 9 parameters, so don't worry, you will see how to do that. So remember in last lab, we used a delay function, and this function is actually defined in already in the library of the AVR microcontrollers. So if we want to use that, we need to pass the parameters, right? So what we were doing, we were calling that function delay from the assembly language, right? But the function is not defined in assembly language, it is defined in the library, right? So how we pass the parameters by using by using these four variables R22, R23, R24, and R25, right? So most significant byte we were placing it in R25 and least significant byte in R22 because this function takes a 32-bit number as a parameter, right? So if we, let's say we are writing a program where we want to pass only one parameter which is of size 1 byte, then we use only R24. We don't use R25. Remember I said they are used in pair. R24 and R25, they are used in a pair as a combination of 16-bit value, right? But if you want to use not 16-bit but only single byte, you place it in R24. You will not place it in R25. R25, you will not even you don't need to load anything, but you need to remember that on the assembly side, when you are reading 1 byte value, you will read only R24, and you need to know that R25 in that case will contain garbage unless you when you are passing 1 byte, before that you set it equal to 0. So to pass 2 byte value, so let's say in our example from A to B, we want to pass a parameter which is of size 2 byte. Then what we do is that we use the complete pair. So we when we on the assembly side, when we will read it, we will read R24 and R25. So the lower byte of the parameter will be in R25 and the higher byte of the parameter will be in R20. Sorry, the lower byte will be in R24 and the higher byte of the parameter will be in R25. So there is another example. Let's say we want to pass nine 1 byte parameters. So then we must use R24 to hold the first parameter, not R25. R22 to hold the second parameter. Note we are not using R23 because we said they are used in pair, but our values are only single bytes, so we don't need to use R23. The next one is like third parameter in R20, the fourth parameter in R18, and so on. Okay. Any questions? No? Okay. Okay, so whenever we are calling a function, let's say we are calling function B from function A. So once the execution of function B is completed, we need to go back to the function A, the caller function, right? And how we do that? By putting return instruction as the last instruction in the body of the function B or the calling function, right? So this instruction actually returns the execution control back to the caller. So this function returns values. We can also return values from the Kali function to the caller function, and for that, we can use up to 8 registers. And what are those registers? R25 down to R18. So let's say if our, let me go back again to, yeah, what, why is not moving downward? There's something wrong, I guess. Okay, maybe I can simply open a new page. What? Just give me 1 minute. Okay. W6D2. Okay. So last time we saw that, okay, if we have two functions, A and B, and A is calling B, then how can we pass the parameters from A to B? Now the question is like, if we have two functions, right? And function A and function B, and now A was calling, so this is caller, and this is calling. Now, at the end, if B needs to return some values back to the caller, so how it can return the values, right? So it can return the values by using 8 registers, R25 down to R18, right? Which basically mean what you do is that you put the values in the first value which you want to return, let's say A, you will put in R25. The second value which you want to return is, let's say, B, you put it in R24 and so on, and then you call return. Okay. Then you put the return instruction at the end. And then it will be the job of the caller to know that, okay, I need to read, if I want to get any values, return value from the B. If I want to get single value, I need to check the content of R25 register. If I want to get two return values, A and B, I will read two registers, R25, R24, and so on. Okay. So, for example, let's say if we want to return 1 byte value 0x24, so uh, sorry. So these registers are again used in pair. So if you want to return a single byte value, 0x24, so you will put it in the R24 register, not in the R25 register. And let's say if you want to return as one value, a single value, but of size 2 bytes, then you, and let's say the value is 0xF024, then you will use the register pair R24 to R25. So you will put the lower byte in R24 and you will put the higher byte in the R25. Okay. Any questions here? Okay, remember I said that there are four different call instructions, there are four different flavors of the call instructions, call, rcall, relative call, indirect call, and extended indirect call. So all of these, the common thing about among all of these instructions is that all of them push on stack the address of the next sequential instruction in the body of the caller function, right? Also, all of them must be coupled with our return instruction to return execution control from Kali to the caller. So that is common, right? But they differ on how PC is loaded and the range of the jump needed to reach the Kali function, right? So the value of PC is determined in different way in all these instructions, and also the range of the address space within which your Kali function can be located is different in all these call instructions. So let's have a look on them one by one. So call instruction, this is a 4-byte instruction, right? And so what happen is that PC is set when you execute this instruction, PC is set equal to operand. So PC operand is basically nothing but the label which is used with this call instruction, the address of the instruction which has that label, right? So if you look at this instruction format here, so you have 22 bits which are used for defining the label or for defining the address, right? So if you have 22-bit operand or 22-bit the field to specify the address, then it's mean that your address can be in range of 0 to 4 uh, mega addresses, right? And how we know that? Because if we have 22 bits, so it is basically equal to 2 raised power 2 into 2 raised power 20, and 2 raised power 20 is mega, and 2 raised power 2 is 4. So it's basically mean that if we have 22 bits, we can we can address 4 mega different locations. So we can specify the destination or the address of the Kali function anywhere within this range. It can be at address 0, it can be at address, let's say, uh, 2 mega or 2 million or 4 mega or whatever, right? So the range basically is huge, like 4 mega locations, right? Now, when we talk about rcall, again, you can compare these instructions same as you compare, like for example, jump and relative jump. In the same way, you can compare call and rcall or relative call. So the bad thing about call instruction is that it consumes 4 bytes. So if you are writing a code, so your 4 bytes will be consumed for by this instruction. Now, the R call instruction, when you compare it with the call instruction, it has smaller size. So as a result, your size of your code will be 2 bytes smaller, and that can be sometimes significant when you are talking about microcontrollers because you are already limited on your code memory. Uh, uh, but the value of the PC, it is not set equal to operand, it is set equal to PC plus 1 plus operand. And operand basically is like the size of uh, the range of the address, which basically is like you have 12 bits in the machine format or in the machine code of this instruction. You have 12 bits to specify the address of the first instruction of the Kali function, and that those 12 bits, they are interpreted as signed operand or as a signed number. So if they are interpreted as signed number, the range of a 12-bit signed number is -2048 to 2047, right? So it's mean that if you have a caller function, again, let me go back and explain. So let's say you are writing a program here, and let's say and then here you say call B, right? And this is an assembly program. And now how far this B can be, and actually this is our call, not our call. How far this call B call the address of the function B can be from the current. it depends upon the value of your 12 bits, right? 12K bits, right? So if the value is positive, it's mean it will be forward as compared to PC plus one. So you will be taking a forward jump. And if the value of these 12 bits or the operand bits is negative, remember we are interpreting it as a signed number, so you will be jumping back. So it's mean that B is somewhere back, not forward. Okay, in your program. Hmm. So execution control, it jumps to the Kali function that is located within this range relative to PC plus one. Now you can if you compare it with the call instruction, you can definitely see that the range of the address within which you can jump as a result of call is limited. It is only 2048 locations backward and 2047 locations forward compared to the current value of the PC. But here you were able to jump anywhere in 4 million or 4 mega location 0 to 4 mega locations anywhere, irrespective of the current value of the PC, independent of the current value of the PC. Other instruction we have is icall or indirect call. So the good thing about this is that it is a 2 byte instruction. So and it is actually the similar in like understanding a syntax as I jump or indirect jump. Just like I jump, it has no operand. And remember in P jump we were using the Z register. In I jump we were using the Z register. The same is the case here. So when you say I call, so your PC is loaded with the value of the Z register, and Z register is 16 bits. So it is basically R31 and R30 and R31. It's difficult to write on slides. So so it's mean that before calling this using this instruction in your program, you need to first load the value of the address where your Kali function is located. You need to a value of that address in R30, lower byte into R30 and higher byte in R31, and then you call then you execute the iCall instruction, right? So Z register must be loaded with 16 address of the Kali function prior to executing iCall. Low 8 bits of the Kali address go to R30 and high to the R31. So since Z is 16-bit, iCall can direct execution control to a Kali function located anywhere within 2 raised power 16, which is basically equal to 64K locations, right? Now, remember we said when we were talking about iJump instruction, we said that when we compare iJump with call and rcall, it gives us the flexibility of dynamically deciding where to jump, right? Depending upon the value we have loaded in the Z register. Same is the case with iCall, right? When I say iCall, so it depends what value I have loaded in the Z register, and then I will start executing code from that instruction, from that address or from that function which is located at that particular address, right? So depending upon, let's say if I'm using a loop and in every iteration of loop, I am updating the value of Z register and then I'm saying iCall. So in every iteration, I will be calling a different function, right? Uh, Again, let me explain what I mean by drawing on this OneNote thing. So let's say here, again, I have, uh, let's say here I'm loading values into Z. I'm not writing the exact code line. Load into Z. Uh, Load function address. Load function address into Z. And then I say iCall. And then I say, okay, here I have something like start. And I say, okay, jump start. So let's say when I execute this loop for the first time, I load the address of function one. Let's say I have multiple functions in my program. Function one, function two, function three, right? So let's say I load the address of function one in Z, and then I say I call, and then control will jump to the function one and it will be executed, right? And when I come back, I say jump start, and again the loop starts executing. And now this time in second iteration, let's say I load the address of the function two, right? So let's say the function three doesn't matter, but let's say we I use function two to keep things simple. So I load the address of function two in Z, and then I say I call. So now this time what is happening? The second function is executed, is invoked, right? And then next, if I load the address of the third function, and then the third iteration, third function, function number three will be iterated, will be executed. So which function will be invoked? It depends upon what value you have loaded in the Z register. So it means by using the same iCall, you can invoke different functions at different times. But this is not possible in, for example, when you say call and then you need to put the label. So label is fixed. Now you need to say call function one. You cannot change it. Similarly, in R call, you have to have a fixed label. So you don't have the flexibility of calling different functions at different time depending upon your need. And this behavior like where you are calling different functions different time is known as uh, implementing function pointers in higher level languages. So this is how you can implement basically function pointers in assembly language. So that is like the advantage of having the iCall instruction. Right? Uh, Remember we said that this instruction actually provides you the range of 64 K location. That is true, but at Mega 328p, we have code memory of only 32 kilobytes. So which means that we can jump the usable range in this particular microcontroller for the iCall instruction is only 32 kilobyte because that is the memory which is implemented on the chip, right? And again, this is the advantage of the iCall that you can implement the function pointers. Any questions? No? Okay, now we have last instruction in the set of in the family of call instruction, which is extended indirect call. Actually, it is exactly same as the iCall instruction. The difference is that iCall instruction, for example, uses 16-bit, right? It uses 16-bit to specify the address, and that's why it has range of 64K location. It can go anywhere in 64K location. But what if my code memory, I have a microcontroller which has code memory of size greater than 32K, greater than 64K, let's say, right? Greater than 64K, then then I cannot use iCall to jump a location which is like beyond 64K address, right? So because I am limited on number of the address bits, I have only 16 bits. If I want to go beyond, I need more bits for specifying the address. And this is what actually eICall makes it possible. So it is 2-byte instruction. Again, it has no operand, but it has how many? 22 uh, it has 22 bits to specify the address. So the lower 16 bits, they come from the Z register, just like iCall instruction, but the upper 6 bits, they come from the EIND instruction. Sorry, EIND register. This register is basically not implemented in at Mega 32 to 328p, but it is implemented in the versions of the AVR microcontroller with larger code memory. So it allows the Kali function to be located anywhere within 4 mega code address space. Since at Mega 328p supports only 32K code address space, eICall is not implemented. So you cannot base actually, if you are running, let's say you are writing an assembly program for Arduino Uno R3, and in the assembly program you use eICall. So most probably your assembler will complain because eICall is not implemented for the microcontroller used by Arduino Uno R3 board. Any questions? No questions? I must be a very wonderful teacher, like able to explain everything in crystal clear way. I hope so. I will tomorrow, I will be able to look at your feedback or evaluation. Let's see how it goes. Okay. So here we have an example where we have 10 minutes, and let's try to go through this example in 10 minutes. So let's say we want to write an assembly program that passes 11 2-byte values from a caller function to the callee, right? So we want to pass 11. Remember, we can pass 9 parameters using registers, but for more than 9, we need to use the stack, right? And then what is the job of the callee? Callee, what it does that then it adds all the parameters together in body of the callee and then returns the sum to the caller, right? So here on left side we have the code, on the right side we have the stack. So I'm setting stack pointer to the highest address 0x7ff, right? And let me quickly walk you through this code. So I am using this equate directive to set temp equal to R4, sum low equal to R5, sum high equal to R6 register. Okay. And here I am simply initializing my stack pointer so that it actually points to 0x7ff. We have seen earlier in the slide what this piece of code is doing, so that's why I'm not going to explain it again. Okay, so now from the caller, so this is the main function, and this function will call the callee or the other function, right? So main function need to pass the parameter. So if it needs to pass the parameter, it needs to put those values in the pair of registers. So let's say the value of the first parameter is 0x1234, right? So what we do is that we put the higher byte in R25 and lower byte in R24. So like R25 has 0x12 and R24 has 0x34, right? So we have loaded first parameter in the pair of R24 and R25. Similarly, we load the next parameter to 0x5678 in pair of R22 and R23. Same goes for parameter 3. This is like straightforward. I don't want to like spend time on these because it's very easy to understand. Third parameter goes to R20 and R21. Same for parameter 4. Similar thing for parameter 4, 5, 6, and 7. 8 and 9, right? So it is straightforward until we reach 9, right? After that, things get a little bit tricky. Now we need to we need to in total pass 11 parameters. So how we can pass the parameter 10th and 11? By pushing them on the stack, right? So let's say the value of our 10th parameter is 0x6633. So what I'm doing is that I am first loading a register, which I have already equated to temp. I don't want to go back in the previous slide, or maybe I can. It is register 4. Okay. So I'm saying load value of 0x66, which is the higher byte of the parameter in the R4 register. And then I'm saying push R4, right? So when I say push R4 and when this instruction is executed and I'm done with that. So what I will see is like I have 0x66 in the stack, and the stack pointer is now moved up to the next empty location. And then but I have pushed only the half of the like upper byte of the parameter. Then I am also need to push the lower byte 0x33 of the parameter. On this I am loading it first in the R4 register, and then I'm saying push the R4 register. So this is what we will see, that now 0x33 is put on the stack and stack pointer is moved. Now we are done with the parameter number 10th. We do the same thing for parameter 11, which is, let's say, has value of 0x7744. So we push 0x774 first put in the register, and then we say push the register. So what will happen is that now we have 0x77 on the stack and stack pointer is moved up. And then we push 0x44 and we see it on the top of the stack and stack pointer is moved. And now we are calling our call sum parameters. We are calling a function, the function which is responsible for summing all the 11 parameters, right? So remember, when we say R call, what happens? That the address of the next instruction in the sequence needs to be loaded on the stack pointer. So what is the address of this next instruction? Address of this R jump end, right? So what will happen? That line 76, I'm just writing line 76. I don't know exact address, so I'm just putting it. I'm indicating it by line 76, and it is put on the stack, and stack pointer is moved up. So now then control moves to, now definitely the PC is loaded with the address of the callee function, which is here. So what does Kali function need to do first? Kali function knows that 9 parameters are in the registers, right? From R25 down to R8. But it also need to read these 2 parameters which are on the stack, right? So how it is going to read them? By what we are going, we are first putting the value of the stack pointer. Remember, stack pointer is a register. It's a 16-bit register consisting of stack pointer low and stack pointer high. What we are going to do is that we load the stack pointer low. We get the write the value of stack pointer low in R28, and we write the value of stack pointer high in R29 registers. But maybe R29 8 and R29 already has some values which we don't want to destroy, right? So we are first pushing their values on the stack. So we are saying push R28. So we have this value of stack pointer is incremented. Then we say, okay, push the value of R29 on stack. So we get this value of R29 on top of the stack pointer incremented. And then we say, okay, now get the value of stack pointer left low in R28 and value of stack pointer high in R29 here, right? So we are simply copying our stack pointer into R28 and R29. So what happens is that now we have stack pointer low in R28 and stack pointer high in R29. So which combined together, these two registers are known as register Y. So this we are indicating here as SP because Y has now the same value as stack pointer register, right? So Y or SP both are pointing to the same location in memory, right? So and then I'm skipping all this code because this is straightforward. You can understand on your own. We are just simply adding the all those registers R24, R25 down to R8, right? And then this is where the things become interesting, right? So here we are first saying uh, load data load indirect data with displacement, which basically means is this, that Y is then a register, add 4 to it, and then use that as an memory address. So this is Y, and we are saying add 4 to it, so it points to this address 0x7f, right? So we are saying read the value from it and put it in R0, right? So in R0 we get 0x44, and then we are saying load the value Y plus 5 into R1, right? So which is this value, and we are putting it in the R1. Now what we are doing is that we are summing R0 and R1 with the sum of all other variables, which the sum of first 9 variables, which we have done in the code here, this code here. Okay. We are accumulating the sum in low and sum in high. Okay. Let me check the time. Okay, we still have like 2 minutes. So we are done with like adding the first 9 and 10th variable parameter. Now we need to add the 11th parameter. So we do exactly the same thing here now. So we say, okay, read the value from Y plus 6, which is this one, Y plus 6 points here. So it gets the value 0x33 into R0. And then we are saying get the value of Y plus 7 into uh, R1, so which is 0x66, and then we do exactly the same thing, add R0 with the low uh, low byte of the accumulated result, and add R1 with the high byte of the accumulated result, and then we get the result. And whatever result we have, we put it in R25 and R24. Remember, we put in these register when we want to return the values, right? So we want to return the result back to the caller. And then once we are done with that, remember we pushed 28 and 29 register. So we pushed them in like we first pushed R28, then R29, and we pop them in reverse order. We first pop R29 and R28. So when we say pop R28, so stack pointer is here. After when we say pop R28, so stack pointer is decremented. It points to this location, which basically means that now when you will say a return, so your PC will be set equal to line 76. Okay, which basically means you will go back to the caller. Any questions here? Okay, even if you have questions, I will be here until end or even after that. But for now, go and do your quiz. And if you have any questions, I will stay after the uh, class time. I'm stopping the recording. Go ahead and do your quiz.